Hello everyone, in this AV we would be starting a new unit known as properties of matter, and first topic that we would be taking up is elasticity. So to understand elasticity, let's take the example of a rubber band. Suppose this is the original size of the rubber band and you apply force at this end and at this end. What do we find? We find that the length has increased, but will the length that has increased, will it be permanent? The answer is no. Once the forces or the applied deforming forces are removed, then it will regain its original length or the shape or the size. Now, this property is known as elasticity. How do we define it? The property of any material, by the virtue of it, firstly, it will oppose any change in its shape and size, and number two, once the deforming force has been removed, it will regain its original shape. So this is known as elasticity. This is the property of a material. By virtue of it, it will oppose any change in its shape and size if you apply the deforming forces, and once the deforming forces have been removed, it will regain its original shape. Now, there can be three types of bodies, namely elastic body or plastic body and rigid bodies. Now, we know the property of elasticity, that once the deforming forces are removed, the body will come back to its original shape or length. Now, elastic bodies are those bodies which have the property of elasticity. That means it will regain its original shape once the deforming forces are removed. Example of elastic bodies could be wet clay or wax, rubber band. These things come under the example of elastic body. Then we have plastic bodies. Plastic bodies are those bodies which do not regain their shape. I mean, when the deforming forces will be applied, they will not change their shape. So if this is a plastic body and we apply any deforming force on it, and after the force is being removed, it will not regain its original size, not regain its original size or length. These type of bodies are known as plastic bodies. And then finally we have the rigid bodies. What are rigid bodies? Whatever the force we apply on them, there is no change in its shape or size, then those bodies will be termed under rigid bodies. Now, what happens in elasticity? If there is a material, then there are particles inside the material. When deforming forces are applied, then this gets stretched. That's how the shape changes. Now there will be three things. It's not that, for example, let's go back to the example of rubber band. You might have seen that initially when you apply deforming forces on a rubber band, the size will increase. Okay, once the size increases, we say that it has change in its shape or in its length. Then we release the deforming forces. Then the rubber band gets back to its original shape. But have you ever thought what will happen if we keep on increasing the force? will it go on increasing in length? The answer is no. There is a certain limit up to which if we apply the force, it will get stretched and then come back to its original shape. But beyond that limit, if we continue to apply the deforming forces, then it will not come back to its original shape. It will rather break. So that limit is known as limit of elasticity. It is the maximum deforming force up to which the body will regain its shape, or we should say it will regain its elasticity. The maximum deforming force up to which a body can regain shape, size or length, or it can retain its property of elasticity. That is known as limit of elasticity. So once the limit of elasticity is crossed, then the body won't be able to retain or regain its original shape. Now this elasticity, if we think about its application in our real life, then it finds its application in, you might have seen the cranes. Cranes are used for lifting heavy loads. So when there will be a rope attached to the crane, that rope will be attracted or will be tied with the load. So once it pulls or picks up the load, then obviously it should be elastic. So the diameter of the rope is decided by the elastic limit of the material of the rope and how much load it can lift. Then second application is for bridges. When we build a bridge, then we have to keep in mind how much load it can take of the traffic. Then it will have its own load. There will be the forces of winds, etc. So it should not bend or break. So these things come under the application of elasticity. Now we talk about stress and strain. Now suppose we have a body and there is some external load applied to it. We have a body and there is a load attached to it. Now this load has a force in downward direction, but there will be, this is the external force, but there will be a force developed inside the material which will be acting opposite to the direction of this external force, and this internal force would try to restore its original shape. Once the load is attached, there will be the change in its shape and size or the length. So this is because of the external force. Then there is an internal force developed which would try to restore its original length. Now this, if we take the ratio of the restoring force per unit area, this ratio is known as the stress. It is the restoring force acting per unit area in the deformed body. Now stress is given as force per unit area. So the unit of stress is, the unit of force is Newton and area is meter square. So the unit of stress is Newton per meter square, and its dimensional formula is given as ml minus 1 t to the power minus 2. Now this stress developed in the body will depend upon how the external forces applied on it. On this basis, there can be increase in its length or change in its length, there can be change in its volume, or there can be change tangentially, or we also call it as shear stress. So let's understand what is stress, then we will talk about these three changes which will be caused because of this load. Now for strain, whenever the load is applied on a body, there will be change in its shape or size. Now this change which has occurred in the size of the body, that is known as strain. The change occurred in the shape or size of the body. Now this change will also be or can be of the same three type, that is, it can change the shape in terms of length, it can change the shape in terms of volume, and it can change the shape in terms of shearing strain. So for longitudinal strain, the formula is, or the definition is, suppose this is a body having the original length L, and when we apply a force or a load, then there is a slight increase in the length and we denote it as delta L. So longitudinal strain is given as change in length upon the actual length. When the deforming force is acting on the volume, then it will be known as volumetric strain or volume strain. Volume strain. So that will be change in volume upon the original volume. And if it's shearing strain, then so that is shear strain is equal to, it is measured as the change in angle between the lines that or those were originally perpendicular. This we will see when we do bulk modulus. Now before we go into the Young's modulus or bulk modulus or modulus of rigidity, in modulus of rigidity we will come across this. So before that, let's talk about Hooke's law. Hooke's law simply says that within the elastic limit, the stress is directly proportional to the strain, but within the elastic limit. Now, and the strain should be small. So if the strain is small, then the stress is directly proportional to the strain within the elastic limits. So this ratio of stress to strain is known as modulus of elasticity, which is denoted as E. Modulus of elasticity. And here please remember that when we talk about strain, it is basically a ratio, so it does not have any unit. Okay, no unit. Strain does not have any unit. Why no unit? Because it's a ratio. When these deforming forces, they act on a body and they act on the body on its length, then the ratio of longitudinal stress to longitudinal strain will be known as the Young's modulus. When these forces act on the volume and we have the ratio of normal stress to volume strain, then the ratio would be known as bulk modulus of elasticity. And if it is the ratio of shearing stress to shearing strain, then E will take the form of modulus of rigidity. So we have, depending upon where this modulus of elasticity works, whether it works along the length or the volume or the shearing stress, then accordingly we will give them the name. If it acts through the length, then it will be Young's modulus. So let's see. If we have a wire and a load is applied, originally the length of the wire was, let's say, L, and because of the application of load, there is a slight increase in the length of the wire. That is denoted as delta L. So you can refer to your book also for this picture. This was the original length, and then after applying the load, this is the increase in the length, that is delta L. So if this is the case, then longitudinal stress is given as force upon area. So force is nothing but mass into acceleration due to gravity, and the area is pi r square. And when we talk about longitudinal strain, then that is nothing but change in length upon original length. Now the ratio of these two, that is the ratio of longitudinal stress to longitudinal strain, is known as the Young's modulus, which is known as, or which is denoted as, Y. So we put the values. Longitudinal stress is mg upon pi r square, and longitudinal strain is delta L upon L. So we have mgl and then pi r square delta L. Now this is known as the Young's modulus. Here also the SI unit for Young's modulus is Newton per meter square. Now it is, this Young's modulus is the property of solids. You might have heard, or if I ask you, which is more elastic, a steel or a rubber? Generally people say that rubber is more elastic than steel, but from physics point of view, when we see it, we find that steel is more elastic than rubber. Why? Because you know that elasticity is the property of the material by the virtue of which, firstly, it will oppose any change in its shape or size which is caused by the external force, and secondly, it will regain its original shape. Now how we decide whether it is which substance is more elastic is by greater the force that we need to produce the change in the size of the body or shape of the body, the more elastic the body will be said to be. So suppose when we have rubber and when we have steel, so if I ask you which one will require a greater force to deform itself, obviously the answer would be steel. For rubber, we require a small force to elongate it, but for steel, a greater force is required to change its shape or size. That is why if we have to produce, like say for example, if we have rubber and steel of the same size, and if we want to produce some elasticity in it, or if we want to change its shape or size, a larger force would be required to or for steel to produce the extension, whereas rubber would require a smaller force. So larger the force required, greater will be the elasticity. That is why we say steel is more elastic than rubber. And by calculation of this, we can show that the Young's modulus for steel is greater than the Young's modulus for rubber. So because of this also, steel is more elastic. Now if a uniform pressure is applied all over the surface of the body, then what happens is the volume of the body changes, but the shape remains unchanged. Now if that is the case, then we say that the normal stress would be given as the force or normal force applied, which is nothing but the pressure, and the volumetric strain or volume strain would be given as change in volume upon the actual volume. Now if the pressure is positive, then the change in volume will be negative, and if the pressure is negative, then the change in volume will be positive. So we put a minus sign here. Now the ratio of normal stress to volumetric strain is what we call as bulk modulus of elasticity, and this bulk modulus is denoted as capital B. So when we put these values, then we have P upon negative delta V upon V, that is equal to PV upon delta V. Now this is the bulk modulus of elasticity, and the SI unit for bulk modulus is Newton per meter square, and the dimensional formula is ml minus 1 t to the power minus 2. Now if we take the reciprocal of bulk modulus, that is 1 upon B, the reciprocal of bulk modulus, then that is known as compressibility, and this compressibility is denoted as beta. So beta is the opposite of bulk modulus of elasticity, so that would be minus delta V upon PV. Now we know that the compressibility of gases is the maximum and that of liquid and solid is comparatively smaller. Now the SI unit for compressibility is just the opposite of bulk modulus, that is meter square per Newton, and here the dimensional formula is m to the power minus 1 L t to the power 2. Now we go to the modulus of rigidity. Now modulus of rigidity, to understand that we have to understand this figure. So we have a body, basically a cuboid, and what we do is we apply a tangential force, a force which is acted on the upper surface, and the lower surface of the cuboid is kept fixed. Then what happens is we find that the upper portion has shifted from A to A prime, and this side from B to B prime, H to H prime, and I to I prime. Now this is the change in the dimension, but the lower portion of the cuboid hasn't changed, it remains fixed. So when we find the ratio of this shearing stress to shearing strain for this, that ratio is known as the modulus of rigidity, and that is denoted as eta. This is modulus of rigidity. So now here we find that there is only a change in the angle, that is theta. So that theta is given as theta is equal to tan theta, and that is equal to B prime and BC, this distance, because we know that tan theta is nothing but opposite by base. So that is B prime upon BC. So that is displacement of the upper surface divided by the distance of the upper surface from the fixed surface. This is basic trigonometry. So here we know that the modulus of rigidity is the ratio of shearing stress to shearing strain. So shearing stress is force per unit area and shearing strain is theta, that is this value, tan theta B prime upon BC. So the modulus of rigidity, or eta, is given as F upon A divided by theta, or F upon A theta. SI unit is Newton per meter square, same like before. The symbol is eta, and dimensional formula is ml minus 1 t to the power 2. Now we will see the Poisson's ratio. Now if we have a body, just look at this figure up to this part. This figure, or this body, is of the length L. Now when we apply a force on the ends of this body, what happens is this gets elongated. Now there is an increase in length, and that increase in length is given as L plus delta L. But what happens is the diameter of this body shrinks. So initially the diameter was capital D, and after the application of force, the diameter has become D minus delta D. This is the effect of the force that we have applied. So the change on the length will be taken as longitudinal strain, and this change within the diameter, that would be taken as lateral strain, and that ratio will be our so-called Poisson's ratio, which is denoted as sigma. So here longitudinal strain is change in length upon actual length, and lateral strain is change in diameter upon actual diameter. So the Poisson's ratio is the ratio of lateral strain to longitudinal strain, that is delta DL upon delta LD. Now there is an important topic, how a wire will behave if we continuously keep on increasing the length or the if we continuously keep on increasing the force or the load. Now we all know that, for example, any elastic material will be elastic within a certain force, that is the limit of elasticity, beyond which if we still keep on continuing to apply the force, then it gets permanently deformed. Okay, and when it gets deformed, this phenomenon occurs. It starts to get thinner and thinner. So for that we have a graph here. This graph is between stress and strain. Now this stress and strain, we have to understand this graph initially from point O to A. Here if you see this line, point O to A, then we find that stress and strain, they are proportional to each other, and that is nothing but Hooke's law. So we say that from the region or from point O to A, Hooke's law is obeyed, and point A is known as the limit of proportionality. Now what we do is we continue to increase the load. So what we find is, beyond point A, if we continue to increase the load, the increase in length will not be proportional to the load or the force that we have applied, but the increase in length will be greater than what force or what load we are applying. So, but still up to point B, the elastic property will remain, and point B will be known as the elastic limit, and from O to B is known as the elastic region. Now if we still go on continuing the load or increasing the load from point B, then at point C comes the situation when even if the load is removed, the material will not regain its original length. And after point C, if we still go on increasing the load, then from point C to D, it is known as the region of plastic or plastic region. Now the wire becomes very thin and the stress is maximum at point D. You can see from the graph the stress is maximum at point D. After that, even if we decrease the load or we remove the load completely, the wire would still go on thinning and it will reach a point E where it will completely break. Now the maximum stress, that is point D, the maximum stress that a wire can bear before breaking, that is known as the tensile stress, and this region C to D is known as our plastic region. Please remember that in this graph, Hooke's law is obeyed only from the region O to A. Now we will see what is the work done in stretching a wire, and that work done will be saved as the elastic potential energy, capital U. So we assume that we have a wire and when it is stretched, work is done against that restoring force or interatomic forces. Now this work will be saved or stored in the wire as the elastic potential energy. So by now we know that longitudinal stress that the wire will go through is given as force per unit area, and the strain is given as the increase in length upon the actual length. So we assume that the increase in length here is not delta L but X. So Young's modulus is stress upon strain, so F upon A divided by X upon L. When we rearrange the terms, we find it to be FL upon AX. So the force which is necessary to increase the length F is from this equation, which says that y is equal to FL upon AX. From here, if we want to find the force, then force is equal to YAX upon L. This is what we have here in this equation. Now, if the length again increases, apart from this increase in length, that is x, we assume that the wire is further increased in length, and that increase is taken as small increase, that is dx. Then work done will be very small work done, which will be given as dw, and work done is equal to force into displacement. So here force is F, the value of which we have already calculated, multiplied by the small length, that is dx. So we simply put the value of F, that is YAX upon L, multiplied by dx. Now, to find out, this is the small amount of work done. To find out the total amount of work done, or the total work done, we have to integrate this equation. So the length goes from L to L plus small l, that is from 0 to L. So we have the total work done is equal to integration 0 to L YAX upon L into dx. Now that we see here, the total work done is equal to integration from 0 to L Young's modulus multiplied by the area into x, that is the increase in length, upon the actual length multiplied by dx. So here we find that these terms y, a and l, they are constant, so cannot be integrated. So we take them out, and we have the integration 0 to L x dx. Now integration of x dx is nothing but x square by 2 from 0 to L. Here we are using this formula. Integration of x to the power n dx is nothing but x to the power n plus 1 upon n plus 1. So here the value of n is 1, so 1 plus 1 is 2 by 2. So this is the work done. Now we substitute the upper limit, then the lower limit. So work done is given as y a l. Instead of x, we will have L square upon 2, or we can write it as, this 2 can be taken out, half y a l square upon L. Now this is what we have here in the book. Now from this step to this step, they have simply rearranged the terms to get stress and strain. Here this, how they have written is, half remains as it is, then we have y they have written upon y, and out of this L square they have taken 1L upon this L, because this will be nothing but stress, and then another L is remaining from here, so that L upon, now we do not have any more L, but for strain we need the increase in length upon the actual length. So this one we are writing extra, so this needs to be balanced here in numerator, so we write, and then we have A remaining. Now if you see, this is what they have done here. So half remains as it is, y, that is the Young's modulus multiplied by increase in length upon the actual length, is nothing but stress. Increase in length upon actual length is strain, multiplied by area into length is nothing but the volume of the wire. And this work done is stored in the wire in form of elastic potential energy, that is U. So that U So this work done is written as U, or the elastic potential energy, is equal to half stress into strain into volume. And if we have unit volume, then this whole term will be 1, and then the elastic potential energy will be half stress into strain only. Thank you.